right? All right. I promised some people, a couple of people yesterday that I would make an announcement. And that announcement is that I wanted to clarify on the homework, there is a, what do I want to call it? Notation that I wanted to make sure that people knew what that meant. So if you see something that looks like this look like something that we've seen or is somewhere, this just stands for the number of A's in the string W. It's a really weird way to state that, but that's how the textbook states that idea. How many A's are in the string W? So if you see something like the number of A's in W mod 3 equals 0, then that's what that stands for. It's divisible by 3. Thought I'd lost my eraser. They just moved it all the way over here. There's another one right in front of my face. There are 2 erasers. All right, we can feed one of them and I'll still be okay. Any other questions I can answer about clarifications on the homework? If you have homework related questions, I would be happy to answer those after class. For those of you who don't know how my office hours work, I just invite everyone from the same class who has similar questions into my office, and that way I'm not wasting your time as there's a line forming outside of the office. So I will try to be as efficient as I can, not waste your time by handling as many questions as I can at the same time. But let's get through as much today as we can so that you can get as much of the homework done over the weekend as you would like to. We're going to start with a really important conversation about the concept of non-determinism. Who has seen this concept in some class or another over time? The actual concept of non-determinism. Couple people?
Me, I've never seen it, but I forgot its exact definition.
Yeah. So everything that we have done so far with our deterministic finite acceptors is that we had a precise transition function from every state given every possible input symbol. And what this means is that no matter what we see in the input string, there is always one and exactly one path to the next state. So that's, if I tie this to experience that you had, every program you've ever written in any language is deterministic by definition. When there is a sequence of instructions that program defines for a particular input, you will always get exactly that same output, and that program will run in exactly the same way with that same input every single time you do it. Again, assuming that you started at exactly the same millisecond. So if you're generating random numbers, for instance, if it's based on time or based on some state of the world, if you started that program at the same time and had a time machine to do that, you could predict, right, the millisecond that it starts. You would know exactly what that output is going to be in advance, or at least you could calculate it and simulate it without actually running the program, assuming that you knew everything about all of the algorithms that it was using, all the calls that it was using. So some examples of determinism. If I asked you to write a program that cracks a password of 6 characters through brute force, my password is exactly 6 characters. It's not, but we'll pretend like it is. So the questions that I could ask you is, in the worst case, how many attempts would it take? Could we place an upper bound on the number of attempts that we would need to be able to crack that password? Let's just for the moment assume that passwords are lowercase letters, uppercase letters, and digits, no symbols. So what would that process look like? How many attempts would it take maximally to do so? We have 26 lowercase letters, 26 uppercase letters, and 10 digits, 0 through 9.
Like 62 to 6 hours.
Yeah, because any characters there, we could repeat them. So yeah, it's just 62 times 62 times 62 times 62 times 62 times 62, 62 to the 6th. That's a large number, but it's not anywhere near infinite or anything that a real computer would struggle with over a long period of time. It would take on the order of seconds to crack this, assuming that we got an instant yes or no and could submit the next one immediately. We weren't locked out, and there was no delay associated with trying to spam brute force this cracked password. The concept of non-determinism now, instead of not knowing the password, I like to think of it in terms of a verification algorithm. So now instead of you're trying to crack my password, I'm going to tell you that my password is 1234556. How long does it take you with proportion to the length of the password to verify yes or no, that is my password? One pass of 6 characters, it would take you, it's linear in proportion to the length of the password. That's how much you have to type in order to be able to determine that. So non-determinism can be thought of as, instead of trying to search for the answer, you are given the answer and then just need to verify the answer. Another way to think of it is you can parallelize all of this. So when I say, what is the first character of my password? Instead of giving you my password, you can parallelize. Instead of typing a single thing, you can, on a different thread, type each of these 62 possible characters. Then when you type the second one, for each of those 62 possible characters, you now press the next character. So we have 62 times 62 threads running now, where each one of those threads has a different 2-character sequence of all possible 2-character beginnings to that password. And then after 6 key presses, you would have 62 to the 6th threads running, each of them trying to check if this password is valid or not. But it would still take a linear amount of time if we had that level of parallelization. So non-deterministically, when we look at a next step, instead of having a single possible next step, we can have a set of possible next steps with the agreement that we're going to explore all of them at the same time, or all of them in parallel. It is a theoretical concept for the most part. This is not something that we can do. But if you've heard of, in an algorithms course or some other place in computer science, the concept of P versus NP, P stands for a polynomial time algorithm, and NP stands for a non-deterministically polynomial time algorithm, which means that an NP says that what is the running time if we could use non-determinism? What is the time of the verification algorithm that runs to determine if you were to give me the answer, how long would it take me to verify that is the answer, or you're lying to me? So instead of the concept of doing a brute force search, we're not looking at these one at a time as a single successor state. We can either assume the correct next state is automatically done, or that we're looking at all possible next steps in parallel. Either one of those is a way to think of non-determinism. Either the guess that you make is the correct guess, or that you're parallelizing all possible guesses. Does that make sense? How are we doing on that process so far? Any questions about that or thoughts? Seems like we definitely need a little bit more work with this, but I think that seeing what a non-deterministic finite acceptor looks like, because again, this is all a theoretical program, or we're theoretically doing what a computer could do. If we could have an infinite amount of parallelization in our algorithms, we could prove or show that anything that we can search for, we could run at the speed of the verification algorithm with an infinite amount of compute power, an infinite number of CPU cores, infinite amount of parallelization. So an example of that non-determinism is to write a program that verifies that a password that's given to you is the correct password. Or it would generate the password through parallelization, where we could use a number of threads equal to all of the possibilities, so that one of those threads would grant you access. If I have a 6-character password, in non-determinism, you would have all of those threads running. One of those threads would allow you access, and all of the others would reject. But the amount of time that it would take for that process, assuming you had that level of parallelization, is linear with proportion to the length of that password. Yeah, one and then two.
If I was gonna write like a really overcomplicated maybe automata for this is like the first node has one guess, but it's 62 guesses, and then each node after that has another 62 guesses and so on.
You would
So
say,
you have-
yeah, when you're trying to read the next character, you would have multiple possible places, next vertices to go to, next states to go to with the same input character read. Yeah, we're gonna talk about exactly how this works in the automata, how the rules change for the construction, but we're actually relaxing quite a few of the constraints of a deterministic finite automata when we do this. And it will allow for kind of an easier solution to some problems, but it turns out that these ideas are actually perfectly equivalent to each other. Non-deterministic finite automata are not any more powerful than deterministic finite automata, which is one of the main reasons that when we look at the P versus NP problem, why it is so difficult, because in theory, they're the same. So how many attempts will it take to verify that the password given to you is the correct password, or to parallelize all of that? It's one attempt, assuming you have that level of parallelization. So you need to crack the password, but rather than searching the entire space, you know which character goes next. You have the parallelization to choose between all 62. So there are, yeah, lots of ways to think about this. If you want to think of it as you guess, but your guesses are always right, or you parallelize and can do all of that searching at the same time. Anything further that I can clarify before we go into, yeah.
Would you hypothetically be able to model an NFA if you had like a quantum computer with enough qubits so that you could just like check all states at the same time?
So the way quantum computers work, it's slightly different. If we explored this space to the level that we needed to, we may be able to model some amount of non-determinism. But based on the number of qubits, what's amazing about non-determinism is in theory, this scales infinitely. And a quantum computer would have a limit to the number of qubits that it can store at a time. So we would be able to say, well, we can parallelize up to this many computations at the same time, having a qubit representing multiple states at the same time. But yeah, we need a way to scale that to not just be 2 or 3 states at the same time, but an infinite number of states at the same time. So we're starting to explore that space with quantum computing, but more work needs to be done for sure. Great question though. So as we did before, we're going to give you the technical definition of an NFA, and then we're going to move into actually what these things are. So the only change between a DFA and an NFA is in the transition function delta. So before we said that this delta was just Q cross epsilon, meaning that for every internal state, for every state in the state machine, we had a number of transitions defined by each character that was in the alphabet. But now, since it's non-deterministic, we're going to allow that to be unioned with a lambda as well, and each arrow for this can be up to 2 to the q, meaning that we can have a number of transitions that are equivalent to each state on each input character could go up to every other state. So many, many, many more transitions are legal than there were in a DFA. I don't fully expect that to make sense yet. The way I want to actually tackle this, so don't worry about having perfect understanding of this going into the next slide. I want to tackle it from the perspective of the actual differences between these two automata types. So assuming that we have a DFA, what changes need to be made to be able to model an NFA? The first one is a lambda transition. We can go from a state to another state without consuming an input character in the string. That's what a lambda transition is. Does that make sense to people? You're able to go, you're kind of able to teleport around. Usually what happened in a DFA is to move from one state to another state, you had to transition on an A or transition on a B. We can now transition on a lambda, and instead of moving to the next character, we stay on the current character. I like to think of it as a teleportation. can also have multiple transitions out of the same state that consume the same character. So this is what that parallelization looks like in this form. So let's say we have state Q0. On an A, we can move to state Q1. In an NFA, we can also say we can move to state Q2 on an A. So now we have two options. Which one do we choose? The right one, and or both, whichever way you want to think of it. If there is a way such that we can end up in a final state, then we choose that way. Do we know that yet? No. So we're doing them both in parallel. Yeah.
Is there any limitation to what states you can move to from a lambda transition?
Nope.
Is it limited to a certain number of states, or can it span all?
Nope, any of them. If we wanna Palpatine it and unlimited power, it's not quite unlimited power, but it's closer than a DFA was. We also don't have to specify every possible transition out of a state. So in a DFA, we had this concept of a trap state, where if you transition to that trap state, that the goal of that trap state was just to say, once you go here, there is no way out. We don't need to specify that in an NFA. If you run into a dead end, you want to be able to consume an A, but there's no possible way to get out of this state consuming an A. There's no outgoing transition. That's okay. We just automatically reject. We don't have to transition to a trap state and continue reading symbols from the input.
There's new annotation for that one.
It's just you don't need to draw an edge. So it does not need to be as complete as a DFA needed to be. This all sounds great. Like it's just a lot more power. So here is an example. Q0 is our accepting state. We can teleport from Q0 to Q2 anytime. Whenever we find ourselves in Q0, we can just, well, we're in Q2. No change to the input string. We just move from there to here. You can see that from Q1, we can either get to Q0 or Q2 on consuming a 0. With a DFA, we had to pick one or the other. We could not have this. So lambda transition. And here we had a multiple edges out of Q1 consuming the same input character. And note that Q2 has no edges out of it whatsoever. Once you're in Q2, if there's another character to read in the input string, we just reject immediately, rather than having to draw a transition out of Q2 to some other trap state. Question?
This will only accept if it's 1-0 forever.
Yes, this is not meant to be a particularly useful or engaging example. It's just meant to give you, this is what it looks like for each of these three differences. But yeah, this literally just accepts the empty string and sequences of 1-0, 1-0, 1-0, 1-0, 1-0, 1-0.
Just wanted to check that.
Yes, yeah,
Why Q2 won't be the final state in this particular case?
because the language that we're accepting from this NFA is just any number of 1-0s, including 0. It's not meant to be useful. But yeah, you can make your final states anywhere. Everything else is exactly the same as a DFA. So you still have a starting state. You still can have any number of final states. Yeah.
What triggers the lambda transition in this?
Parallelization. So you're going to both, anytime you find yourself in Q0, you're both in Q0 and in Q2 at the same time. Or if there's a way for the input string to be accepted, you're going to choose the direction that leads to that acceptance. But now there can be multiple different paths, some of which end in acceptance, and some of them do not end in acceptance. And we will say we accept this input string as part of the language if there exist one or more paths to a final state. So maybe there are 10,000 paths through this. One of them is accepted, 9,999 of them are rejected. We accept that as part of the string, just like the verification of a password. We cracked that password if we can parallelize the 62 to the 5th possibilities, and one of them allows us access. It doesn't matter that the rest of those paths led to something incorrect that didn't allow us entrance. Yeah.
So if you were just looking at like 1-0 and you were at Q1, you would pick the path that goes back to Q0 because that's the one that.
Yes. Yeah, if you're in Q1 and there's, yeah, two paths, this is, you can take that 0 or this 0.
But you're kind of in both of them, but.
Yeah,
Okay,
yeah, you can think of this as either pick the one that leads to success. This one's not going to lead to success, so we ignore it. This one is going to lead to success, so we're going to do it. Or you can think of it as we're doing both of them, and since at least one of them leads to success, we accept.
Okay.
Either one of those were the equivalent logic for the sake of non-determinism. So it's really cool when you think about it as a theoretical concept. Imagine having the ability to write programs that were non-deterministic in nature. This is why P versus NP is such an interesting problem. If we can generate an algorithm with a non-deterministically polynomial time algorithm, so something that is not exponential in nature, non-deterministically, can we generate a polynomial time algorithm for that, a polynomial time deterministic algorithm? We have no proof either way that either we can or we can't. And the concept of NP complete, if you've heard of NP completeness, that is an entire set of algorithms that if we can ever show that there is a polynomial time deterministic algorithm for one of them, then there's a polynomial time deterministic algorithm for all of them. And then we've shown that P and NP are actually the same, which would be both amazing and really scary, because the entire security of the internet is based on the concept that P is not equal to NP. If it ever is, if that is ever shown, take all of your money out of all of your banks. Just hoard everything. Do not store anything on the internet. Nothing is safe. Nothing is sacred. Everything is public.
Quantumly insecure algorithms we use, it's fine.
Pay attention to the news. The world will start burning if P is equal to, if we ever show P is equal to NP.
Just RSA would be out the window completely.
Yes.
To use something else, it's the big problem.
You have to use something that is not, it's more complicated than exponential. So why do we care to study non-determinism? Why is this even remotely? I've kind of talked about this so far, but if computers and algorithms that we've all written are all deterministic in nature, why do we care about non-determinism? But many problems have easier non-deterministic solutions than deterministic solutions. So you can actually make a simpler state machine and a simpler algorithm via non-determinism than determinism. So if we ever show that P is equal to NP or develop quantum computing to the level where we could actually start to simulate some basic non-determinism, then currently difficult problems become much easier and much faster. Later on, within the next couple of days, we'll actually show that there is perfect equivalence between NFAs and DFAs. So if you are really struggling when a question asks, prove that this language is regular, if you can find an NFA for it, using the proof that for every NFA there is an equivalent DFA, you can now show that by writing an NFA, I've also shown this language is regular. So it becomes yet another way to show that. An example of this is search and backtrack. So think of something like depth first search. You search, and if you fail to find, then you backtrack until there's some path that you haven't explored yet, and then you explore down that path. Non-determinism just says we're exploring both of those at the same time. There's no backtrack, it's just search. And it becomes the depth of the tree is how long it takes, rather than the total number of nodes in the tree. And you know that the number of nodes in a tree is exponentially proportional to the depth of the tree. We've taken an exponential problem and turned it into a logarithmic problem. That's a huge difference. Huge difference. So optimizing search and backtrack, if you could somehow just make the choice that is going to reach the goal, whenever you have a choice, left or right, well, whichever one gets us to the goal faster. You never know that in the middle of an algorithm, but non-deterministically, we'd be doing both of them at the same time. So you're always choosing the one that gets you there fastest. So yeah, non-determinism, rather than using worst case analysis like you have thinking about big O notation, you're able to parallelize it to say, well, it's always gonna be the same amount of work, because you don't ever have to backtrack. I've also talked about P equals NP is the biggest open problem in computer science. I don't know if you're aware that there is a $1 million prize available to anyone who proves either P equals NP or P does not equal NP. So show this, you will not only be able to kick every computer scientist of the last decades who have been trying to solve this problem, but you would also show that it's true, break the internet. And if you show that it's not true, then, yeah.
How can there be an equivalent DFA for every NFA, but we don't know if P is equal to NP?
Because we're just talking about regular languages here. This
Okay,
will
so
not be the
there's no-
same
yeah.
when we talk about other classes of languages.
Okay, I understand.
Yeah, it's a great question though. Otherwise, it would be equivalent. It is equivalent at the regular language level, but it's not equivalent at the next level that we will talk about. So we already talked about this. Solvable non-deterministically in polynomial time. Are they able to be solved deterministically in polynomial time? That's an open question. Talked about NP completeness. No proof exists one way or the other. If you solve it, you become an instant millionaire. Not that that means much anymore. $1 million 2 decades ago meant a lot more than $1 million today. We'll actually study this in a lot more depth later on when we talk about the actual theory of computation. What is that limit between, assuming we don't have quantum computers or meaningful quantum computers, what is the limit of deterministic calculation? We're going to explore that boundary in a lot of detail. You get non-determinism in grammars. Whenever you use that exclusive or, the vertical bar, we can apply one rule or the other. Which one do you apply? Well, if you can go down some path to be able to produce the string that you're looking for, then congratulations, you've shown that a particular string is a sentence in this language. But deterministically, we would have to actually go search. What happens if we apply the production of the production from before the or versus the production after the or? Deterministically, you're searching, you have to do both. Non-deterministically, you do both. All right, let's start thinking about designing NFAs. So remember those 3 important rules. Lambda transitions are okay. We can have multiple edges out of a state that consume the same input character. What was the third one? Yes, so you don't have to write trap states or anything else that you don't want to. If it doesn't lead you to an acceptance or a possible acceptance, you do not need to include it in the NFA. So the language is some number of A's such that n is greater than or equal to 3 or more A's, as well as AB A to the n such that this n is greater than or equal to 1. So it's a unioned language. You see your first A. That's all you've read so far. Are you in this world or are you in this world? This union specifies 2 different languages. You see just the first A of a string. Should you start looking for more A's or should you be looking for B A to the n? Deterministically, you have to choose. Non-deterministically, we can explore both at the same time. So think about that as you construct your NFA. Feel free to talk to people around you as you work through this. This may help you get started if you're struggling.
Oh, okay.
Hey, I actually kind of did that. I figured if we can explore two things at once, why stop with one arrow?
Those are like two things, two words in front of you or something. Okay.
I can see how close I am. So,
So DFA inherently an NFA.
So every NFA has an equivalent DFA. Every DFA can have an unlimited number of equivalent NFAs. So we will show a process of converting an NFA to a DFA in a day or two, but they have the same actual power.
Well, I guess I just mean that like if you make a DFA, is that technically also an NFA?
Yes. Yeah. Yeah, an NFA is just a more vague, more broad concept. Yeah.
For the nodes coming off the branches, does it still follow the path of like Q1, Q2, Q3, and then you get to L2 land, it's Q4, Q5, or can they?
Does not matter. Whatever makes more sense to you. You can even have a Q1 L1 and a Q1 L2. They're not named the same, but you would append the L1 and the L2 to each of those names to show that there's a separate sequence here that we're exploring in parallel. For those of you who have finished with the first, I think this is going to overlap my L1 land just a little bit. You can start working on a second problem. If you're still working on the first, no problem. I just want to give everyone something to do.
It's mainly just like the end stuff that's like, I guess.
Yeah, let's draw out a whole solution to the first one here in a second.
I guess I'm not sure like how I like. How many hands specifically or like in order to like.
Yeah,
it's union, so one for the other is a valid path.
Yeah.
And as soon as you see one, then it's valid in the language.
yeah. These unions are really difficult to consider with a DFA. But we will find that the union is no problem at all for an NFA. So languages that have this design of a union
Because you're always.
it should immediately make you think, NFA, I want to design an NFA for this. And it will actually probably be less work for you to design the NFA and then convert it into a DFA than it will be to come up with the DFA logically from scratch.
Yeah.
Right. Because DFA would be better for like across, where it's exclusively this narrow region.
Yes. So here's L1 land. Remember that we don't need to specify what happens if we see a B. In the DFA, we needed to make a trap state for this. With an NFA, we do not.
Wait, why do we have to specify PCV? Because I thought you had to have the combination of the two ultimately, right?
Yeah, we haven't finished L2
Oh,
land yet at
okay.
all. But if we're in L1 land and we see a B in the middle of this, as we're parallelized exploring both, we see a B, we just automatically reject. We're not in L1 land at this point. AAB, nope. AB, not in L1 land.
That exponent got me again. Cause I was thinking like, okay, that's a multiple of an A. And I was like, okay, the same time, I was like, oh, it's not.
I'm gonna call this Q4, you can call this whatever you want. So now we need to see a B for sure, going to Q5. But once we see, since this is A, we need at least one A here, we would have this to be an A. So this, I think, is the most intuitive way to view this NFA, but we can actually remove one of the vertices from it. Does anyone see what we can do to make this simpler? Let's go here, yeah.
You can take the, well, first split with the A where it goes down, you can just use the first A down the top one.
Yeah, yeah,
So you get rid
so
of Q
once
one.
you've seen this, this A can now map here instead of here, because this is exactly the same transition on an A, transition back to itself on an A.
I was saying closer to the start on the left, so
Here?
that one you can get rid of, you can just go to the A.
Since Q1.
Yeah, if we, Q1, we see that first A regardless.
Yes.
Now we can either do an A here or a B here.
Yes.
Yeah, and then go back to, that would be
And
even
you can
simpler.
also-
Yes, so none of these ideas are wrong. If you put any of these in a homework, it's correct. Unless it asks for a minimal structure.
What if the second language is into the, or if n equals 2? So if you want A, B, A, B, A, would that still work?
So which one, where?
Right there. Language 2, the
Language
top
two?
one. Or sorry,
Language
language
two
1,
of
the
the top
second
one,
part.
yeah, A, B, and then what?
If it was N2, so wouldn't it be A, B, A?
A, B, A, we just go back to Q6.
But then don't you need the other B and A after that too?
If we, so this is the ABA, that we need to see for the n equals 1.
Yeah.
So let me write down your example. What's the example that you're,
If it's A, B, A, B,
yeah. So we'll go down, A, we explore both. So we're kind of at the same time in Q1 and Q4. We see the B, this path drops. We can't possibly get a B out of here, but we can from here. The A is here, the A is here, so now we've seen the first 4 characters, but then there's no way to get from a B from here, so we drop that. We're not terminating in this accepting state, we are immediately rejecting, because in order to accept, we both have to be in a final state and at the end of the input string. So if we have not reached the end of the input string and we see a character that we cannot deal with from this location, then we immediately reject regardless of where we are. So it's at this B that there is no valid path to a final state while we are at the end of this string.
Is that N saying for just that last A or just, well, is it the whole pattern?
Don't know if I quite know what you mean.
So
This,
for
this
the-
A here,
The N,
oh, yeah, up here.
yeah,
Yeah, this just says repeat this A.
Oh,
We need
okay.
one or more of these A's here. Yeah.
That was like the whole ABA.
Yeah, that's what-
times.
Oh,
that's why.
yeah,
I
no,
was
it's
like-
just A to the N. If there's any more than this, there will be, since exponents have a higher precedence than concatenation, then yeah, this is A to the N, not ABA to the N.
I thought it was ABA to the end.
Gotcha, yeah, I should clarify that. Yeah, the exponent has higher precedence, so it's only attached to the most recent thing unless there are further parentheses. If it were ABA to the N, it would be represented as such. Great clarification.
Can I ask you a quick clarification?
Yeah.
So like, so long as there's like, I guess like, what is it, like a string that like results in, that results in everything going to like the end path, then it counts, if that makes sense?
Yeah. So I think I understand what you mean. Basically, when we get to this end, we have to also be at the end of the string.
Yeah, it's like, okay, yeah, it's like, I guess I'm just, yeah, sorry, it's like it works if both of them are like at the end of the string, right? It's just like.
Yeah.
sometimes it is.
Yeah, we're looking for one or more paths to acceptance.
Okay.
And it's okay if we get one path to acceptance and 10 paths to rejection, we still accept. But we need that one path to acceptance. How about the second one? How much time we have? We have enough.
Don't know what I have and
Talk to me about it.
okay, so since we can have b greater than or b to the n, where n is greater than 0, that means 1, meaning we don't even technically need anything as long as it's precedent. So
0 or more of these.
as long as we have a b, it's a final.
Yeah.
State.
Yeah. So again, I like to break this down into L1 and L2. If we can find some commonalities between them, that's great. But for the moment, I'm just going to treat them as completely separate. We're going to have a path through the first half and a path for the second half. They do both consume an A at the beginning. However, this A, the first A, leads to acceptance because 1 is odd. Whereas here, we don't have acceptance yet. So in this case, we do actually need 2 separate paths for the A. We can't just have a single path through the A because one of them leads to acceptance in the first half and one of them does not for the second half. Yeah,
So would you just have it just cycle to that first node?
I would. We're gonna actually run into an issue if we do that. Let's take a look at what that would look like. So we're gonna say that Q1 is an accepting state because 1 is odd. If you cycle back to this on an A, what happens if you go A, and then down the L2 path? That's gonna create an issue. Because none of these starts with AA. And that would mean that there's a path to acceptance by doing that. So that's a great idea, but it will lead you down the wrong path. So we are instead going to make an even one out here. That is Q2, that comes back here on an A. So now if you see 1 or 3 or 5 or 7 or 9, then we get the acceptance from L1. To do this one, we need an A that does not lead to acceptance, followed by a B that leads to acceptance, because AB with none of these B to the N's is technically in the language, so this needs to accept, and then we need to be able to accept any number of more B's, so we will circle back around to this on more B's. And again, we don't need to draw any more transitions than this for an NFA. So this is complete and done.
Is that minimal? Are there any things you can take out?
I do not believe so, although we will have the tools to be able to do that in a bit. Question?
Doesn't that accept A, E?
This does accept AB, but AB is in the language. If N is 0, we want AB, B to the 0, which is lambda. That should be in the language. Great clarification though. Questions on design of NFA? Yeah.
Oh, why can't we run a B edge out of Q1 to Q4?
If we did this as a B,
Yeah, why can't we do that?
because, yeah, no, actually that would work. That would work. If we do this B here, rather than all of this. Because A is accepted, because it's the union of this language. Except then, what happens if we do A, B? Is that in the language?
Oh, right, okay.
No. So, yeah, that's the counterexample where that breaks. Good point. I did have to get there myself. It looked good from the beginning. But you will see how very quickly and easily a solution that seems like it works falls apart with just a single little counterexample.
Will it not work? Because A to then would be odd, then we have a single B, the precedence.
Well,
and then the
yeah, we
substring of
need
AB.
one or the other of these. So is there the possibility of an B being accepted in this string? It's not A to the N, since there's a B at the end. And it's not B to the N, because the second character is an A. So it's not in either one of these languages. that are being unioned together.
Mentioned that, you could like go, you could like split later if they started the same.
Yeah,
Wouldn't you just not write that in the definition of the language since it's like an implied start?
what do you mean by an implied start?
Well, like, you're gonna see these characters.
Right. It's just that you would, if there exists a path to acceptance, then you accept. So this string that's not in that language, if we had this arrow, this would get accepted because there would be a path to an acceptance from that structure. And we should not accept this. We need it to be a failure. So we need to make a design where it is not possible to get to a final state from this string. Any other questions with the 1 minute we have left in class? I am not going to start us down the road of NFA to DFA conversion with 1 minute to go, but that is the next thing we're going to be talking about on Monday is given that we have an NFA, how do we convert it to a DFA? Yeah, any homework questions? I'm happy to answer in my office. I will be up there for at least the next hour.
I think uploaded all the slides, yeah.
Yes, through the start of what we covered today. Today's are not up, yes, but I can get it. Yeah.
Yeah. If one of them.
The first.
Works, then it's just.
Yeah, then we accept.
Okay, so one is number 4. It doesn't matter if it's one of them.
Of course, for some reason, getting like.
Yeah.
Hard time calling these fun,
Like if there's only.
I'm pretty sure there's
There's only just
like each node is its own principle.
I thought we were just
Yeah.
right.
Yeah, even though that way you are.
I didn't read the circles when I first did it.
Oh, so you just wrote.
I just wrote the concepts and I'm like, wait, how do I write this?
Yeah.
Right.
If I get that and I can work backwards, I'm
Yeah.
fine.